So just a little recap. Right now, today we've learned basic I/O, so how to interact with files, reading and writing, so reading from files, writing to files. We also learned how to do these I/O operations on in-memory buffers, so without dealing with files. When we'll be doing assembly, we're really hacked for assembly. We will do this, so after I do the Python, we're going to go into C. And as we go into C, I'm going to introduce some assembly as well. And then we're going to get really into the assembly. It's going to be really interesting. So the basic I/O is learned. String formatting, so basically how to deal with strings, how to represent strings and represent expressions and variables inside of those strings. We've learned that too. Now we're going into bases. And why is this important? What are bases? And this is actually where I'm going to probably full screen this because I think I have to start because it's just simpler to draw diagrams and stuff. So, okay, this is really not comfortable. Okay, so what's a base system? Or what's a numerical base system? Every time we count something, we usually use base 10, right? So let's start with base 10. And what does that mean? Well, base 10 is a numerical system where where it is consisted of 10 digits, right? That's why it's called base 10. There are only 10 base digits, which are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9, right? These are the base digits. That's why it's called base 10, because there are 10 of them. Now, when you count, you go from 0 to 1, then 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and after 9, you go to 10, right? 10 is not a digit anymore. 10 is composed by two digits, the digit 1 and the digit 0, right? That's why it's not a base digit. And this is really how you count, right? And why do you go to 10? So let's look at it in a different way. So you have, again, 1, you have 2, you have 3, you have 4. Let's continue here. You have 5, 6, 7, 8. Let's continue here. You have 9. And then when you get to 10, what you're really doing is you're putting a 0 here, and you're saying this is 9, this is 0, 9, because it's the same thing. It's actually what you're doing, right? You just don't write the 0 because it doesn't matter. And now that we have no numbers on this side, because after 9 there's nothing again, this goes into 0, because after 9 there's 0. So you loop around, this becomes 0. And of course, this has to be incremented. Oops. So this becomes 10, right? Oops, so 9, 10. Now, afterwards, so 11, 12, again, we're always incrementing this number until, of course, we get to 19. Now, when we increment this number, there's no digit after this, so it goes back around into 0. So this becomes 0. And of course, we have to still increment this one, so this becomes 20, 21, etc. Until we go to until we go to 99. Right? Now, if we increment this one, it becomes 0. If we increment this one, it becomes 0. But don't forget, the 99 is 0, 99, right? So when we increment this one, it becomes 1. So this is 100. So then 101, etc. And this is how we count, right? I guess people understand how we count. Now, this can be applied in any base. So we just happen to count in base 10 normally, because that's what we started doing. We defined the 10 digits. But we can do this in any base. So let's pretend that we're now in base 4, right? So what is base 4? So hello, hey Elementa, how you doing, man? How you doing? We didn't cover that much. We actually did cover quite a bit. I was just explaining base 10. So we're going into bases. I'm good, thank you. Oh, that's awesome. But yeah, just for some context, just for some context, I was just explaining base 10, so how we count in it, right? So we have 0 through 10, and, sorry, 0 through 9. And as we go into 10, right, we start reusing the digits that we used before and always incrementing them, right? And it's the same thing when we go into base 4, any kind of base, actually. So what are the digits of base 4? Base 4, as the name suggests, has 4 digits, right? 4 basic digits. So it has 0, 1, 2, and 3. These are 4 digits. This makes up base 4. So how do you count in base 4? Well, let's start with 0, then 1, then 2, then 3, and there is no 4, right? Because the digits of base 4 is from 0 to 3, so there is no 4. So when we get into here, and we increment 3, it goes back around, right, into 0. But again, remember that this is the same thing as saying 0, 3, right? So this is what we're doing, and we're still incrementing this one. So now it becomes 10, right? And then let's continue here, 11, 12, 13, and then we cannot increment this further to be 4 because there's no 4. So when we increment this, it becomes 0. And when we increment this, it becomes 2, right? Then 21. Wait, I actually erased it. I didn't mean to erase it because obviously it's the continuation. So 22, again, 23. There's no 24 because it just goes into 0, 2 goes into 3, so it becomes 30, 31, 32, 33. And now we reach another problem, right? If we increment this one, it's 0. If we increment this one, it's 0. But again, don't forget that you have a 0 here, right? So when you increment this, it's 1. So this becomes 100. So this is like how you count in base 4, right? And it's the same concept as base 10, except you're limiting your digits to 0 through to 0 through damn it. You're limiting your digits through to 0 through 3. Right, and you're doing so your digits will always be so you have a base 4. Your digits are always going to be mod 4, right? So what this means is you start with 0, then you go to 1, then 2, then 3, and then you go back into 0, and then 1, and then 2, and then 3, you go back into 0, 1, 2, 3, right? And that's why we've been, you know, when you reach, say, 13, this 3 goes into 0, right? And this 1 goes into 2. And once you get to 33, these 2 go into 0, and then this other number goes into 1. So this is how we count. Now, why is this useful at all? Why not just do everything in base 10? Well, it's useful because we can do mathematics with it. And we can also do it in base 10. It's just it becomes harder depending on what environment we're in. So for example, let's do so let's say we're in base 4, right? Base 4. And also, okay, let me do something else which is going to become a bit clearer. When you have a number like 1010, do you guys have merge? Yeah, we do. Let me just show you really quickly. So if you go into there we go. So whitehathacking.tech, we have a little merge link. We have a really cool merge. We have more merge coming out as well. Okay, a little side note. Sorry. Okay, again. So let's say we have a number, and this number is 1010, right? 1010. And this number is base 10. What does this mean? You might have learned in high school that you can separate the different units of the different digits of a particular number into certain places. So for example, this, wait, let me do this larger. So 1, 0, 0, 1010. You probably learned that this can be separated into, let's say this is the ones, this is the tens, this is the hundreds, and this is the thousands, right? Are you guys familiar with this? You probably learned this in high school. So you have the ones, the tens, the hundreds, and the thousands. And this makes sense, right? Because obviously this is the ones. Yeah, it makes sense. Why? And why is it called this? And what are we doing? What does this mean? Well, this actually has a very particular meaning, and there's a very specific reason why these are called the ones, the tens, the hundreds, the thousands. And this is because what you're really doing when you are representing a number in any base, in any base, it just happens that this is base 10. What you're doing is you're taking that base and you're saying, well, this first digit is our base raised to the power of 0 times that. The second digit is 10 raised to the power of 1, 10 raised to the power of 2, 10 raised to the power of 3, etc. Right? If you had a larger digit, a larger number, you would do this for larger. You would continue, right? So you start at the left side, you go into right. You start at the right side, you go into the left side. You start with 0, and then you just increment it. And what this number means, what 1010 means, it means the result of multiplying 1 times 10 to the power of 3 plus 0 times 10 to the power of 2 plus 1 times 10 to the power of 1 plus 0 times 10 to the power of 0. Right? And the reason why this becomes the ones, the tens, the thousands, the etc., the hundreds and the thousands, etc., is because, well, what is 10 to the power of 0? 10 to the power of 0 equals 1. 10 to the power of 1 equals 10. 10 to the power of 2 is equals 100. 10 to the power of 3 equals 1,000, right? So that's what you're doing. So this is the ones because you're multiplying by 1. This is the So this is the ones because you're multiplying by 10 to the power of 0, which is 1. This is the tens. You're multiplying by 10 to the power of 1, which is 10. Again, hundreds, thousands, etc. And the result of this is your number. So 1 times 10 to the power of 3 is 1,000. So this is 1,000. Plus, well, 0 times any number is 0. So plus 0. Plus 1 times 10 to the power of 1, which is 10. Plus, again, 0 times something, 0. So this equals 1,010. So this is your number, right? And this is the same thing in any base, except the difference is instead of having 10 here, you have your base. So let me, I can clear it better like this. So let's say we have, again, let's say we have base 4, right? And you have the number 200. So what you're doing is you're doing 4 to the power of 0 here, 4 to the power of 1, 4 to the power of 2. So instead of calling it the ones, the tens, the hundreds, what you're going to actually call this is you're going to call it, well, technically you should call it, the ones, you call it the 4s, you call it 16s, right? Because these are the results of these numbers. So now if we do this multiplication and add this together, we're going to get us 2 times 16 plus 0 times 4 plus 0 times, right? Which is going to be 32. So the number 200 is the representation of 32. And how can we actually see this? Well, we can count it, right? So it might take a while because 32, but let's we know it requires 3 digits, so let's start with 0. So this is 0, and I'm going to erase it, but every time I erase it, I'm going to make it obvious, I believe. So 0. This is 0. You know what? Let's just do it in a different way. So 0, 0, 0. This is 0, right? 1. This is 1. 2. This is 2. 3. This is 3. 0. Again, remember. So when we increase this, of course, it's going to go into 0. So now we have to increase the next one. So 1. So it's going to be 4. And this is the representation in decimal, right? We're just counting it in decimal, and this is base 4. So, 0, 1, 1 would be 5, 0, 1, 2 would be 6, 0, 1, 3 would be 7. Hope I'm not making any mistakes right now, but then 0, 20 would be 8, then 0, 21, 9, 22, 10, 23, 11, 30, 12, etc. And then and you would continue this until you get to 200. It's going to take a while, and 200 would be 32. Now, I can do this with a lower number just so you can get it. So we know that 30 is 12, right? For example, we just realized that 30 is 12. So let's stop here, and let's deal with this 30. So we know that 30 in base 4 is 12. So what are we doing when we're doing in base 4? So 30, we have our 4 to the power of 0, 4 to the power of 1. Oh, this is actually wrong. It's not. I'm an idiot. Am I? No, it is. Oh, wow. I just brain farted. First, so again, we're multiplying these. So 3 times 4 to the power of 1, which is 12, plus 0 times 4 to the power of 0, which equals 12. So we can see that this is 12. Which number that ends with 4 is 0? Yes, this is what I was trying to say before. It might be a little bit of a difficult concept to get at first, but here's the idea, right? So your numbering system starts with digits, right? This is your entire known. And oops, this is not showing anymore. Why is it not showing anymore? Oh, it's lagging. Okay, this should, okay, it's lagging, but it's back now, I think. Okay, so why is this, okay, so this is base 4, right? Your whole known world are these 3 digits, are these 4 digits. So to compose numbers, you start with the lowest of them all. So you start with 0. Then to increase this, you add, so it goes into 1, and it goes into 2, and it goes into 3. Now, and here's the thing, these are the only digits that you know. When you start after 3, the next digit is not a base digit, so you have to combine digits. And which digits do you combine with? Well, if you want the next lowest number, you have to combine it with the next lowest digit. Of course, the next lowest digit after 3 is 0, right? Now, of course, if you just put 0, you're back where you started. So you have to add something to the left of it. And if you remember, 3 is the same thing as 0, 3, right? Which is what you're representing. So the lowest number after 3 is 0, but the lowest number after 0 is 1. So that's why you go into 10 here, right? It's a modular, it's a mod operation. So you're going into here, and then you're going back down. And here you're going to here, and you're going back down, right? So 3 is your limiter. Anything after 3 goes into 0. Yeah, it's a way of counting. Yeah, it's just the way you count, right? It's the way you represent it, because 10 here is obviously the lowest number after 3, right? Because 4 does not exist, right? So this would have to be 0. And if you do, for example, 13, right, that's going to be after 10. So 10 is the lowest number after 3. That's the idea. So, and yeah, so if you're, and this is how you represent, next would be 11, 12, 13, then 20. Yeah, exactly. So 11, 12, 13, and then, of course, 20. Like this, the 3, of course, the next one would be 0, and then we have 20. Right, and it's the same thing as if, as soon as you go into, well, there's no 9, right? But if you go into 33, well, you were 33, the next would be 100, right? It's the same idea, the same concept. And you do this in any base. This is base 4, but you can do this in base 2, base 3, whatever you want. No problem. And why is this important? Well, because you can do mathematics with it, right? So let's say 12 times 2. This is 24, right? 12 times 2 is 24. Well, and this is a fact. 12 times 2 is 24. Let's look at what 12, so let's look at base 4, right? So let's say that this is in base 4. We're doing this in base 4. What is 12 in base 4? Well, we'll just learn how to look that up. So 12, we're going to have our exponents. So we're going to have 4 to the 0, 4 to the 1. And this is going to be equal to 1 times 4 to the 1 plus 2 times 4 to the 0, which is going to be 4 plus 2, which is going to be 6, right? So this is 6. So we know that this is 6. Assuming I didn't do any stupid mistakes, this should be 6, right? And then 2, in base 4, 2 is just 2, right? Because if you do the 2 number, right, 2, and then you use your exponent, right, so you do your 4 to the power of 0, all you're going to get here is going to be 2 times 4 to the power of 0, which is 1, so it's 2. So 2 is just 2. So 6 times 2 equals 12 in decimal. Right? Now, if you do the same thing with 24, where you figure out what this is in decimal, right? So you have your 4 to the 0, your 4 to the 1, and then you look at this, and so 4 to the 1 is 4, so 2 times 4 plus 4 times 1, so that's 4, which is 12. So at this point, you realize that it's the same thing, right? So 12 times 2 equals 24 in base 4, right? But 12 times 2 also equals a 24, well, 6 times 2 equals 12, in this case in decimal. You can, obviously, the mathematical relationship, like the mathematics is preserved, right? You can do mathematics in all kinds of bases, and the answer is the same across all bases. You just have to convert the numbers to those bases. And this becomes really, really useful because when you're dealing with systems of information or systems where you're dealing with let's say binary states, or let's go into electronics. It's good for base 16 notation. Oh, base 16. Okay, let's talk a little bit about base 16. Base 16 is pretty useful too, and this is something I should have talked to before as well, because for base 2 or base 3, you can use the digits that we normally know. But for base 16, so we have 0 through 9, right? And after 9, you cannot use 10 because this is 2 digits, right? So we have to come up with different digits because it has to have 16 digits, right? So then we come up with A, we come up with B, come up with C, come up with D, E, and F, right? And again, 0 through 9 makes 10, so 0 through 9 is 10, 11, 12, 13, 14, 15, 16. And this is 16 digits in total. Hey, Neox, what's up? Yeah, for assembly, right? For a lot of purposes, not just assembly. But I'll get to it. Now, why is this important? Well, why is base 16 even used? Well, working in different bases is really useful depending on the environment that you're in the system, in the world that you're in. Let's say that you are working with binary data, right? You're working with binary data. So let's just go into that. So you have electronic components, right? So we talked about this before in the very beginning, but it doesn't really matter too much right now. But the idea, oops, I forgot the light bulb. Let's put a light bulb here. So this is a little light bulb. It's connected to this. And this is a switch, okay? And you don't really need to know anything about this. Let's just pretend like this is just power. If you don't know anything about circuits, this is just the power. This is electricity going through, right? And this is a switch. What this means is, right now it's disconnected. So, you see these are basically, think of it as cables of electricity, right? But this is not connected, right? So electricity does not flow from here. It does not flow to there because it's not connected. But when you push the button, it becomes closed. And then it connects. And as it becomes closed, electricity passes through here. So that's what a switch is, right? So first, it's when the light is off, the switch is open, so electricity, is coming, and it's actually not passing here, so it never reaches the light bulb, right? Even if you consider the electricity comes through here, it never closes the circuit, right? So if it never closes the circuit, the light bulb will never light up. But when you click on the switch, this will close, right? And suddenly you have light on the light bulb. Okay? Pretty simple idea here. And that's it. The signal that you get from this is either it's closed or it's open, right? It's either closed or it's either open. So it's either 1 or it's either 0, right? Either the electricity passes through it or it does not. And this is a binary system. If you gather information like this, it's a binary system because the only answers are 1 or 0. Red's there in a different color. Red seems a bit weird. So it's either 1 or it's 0. And this is why binary comes in handy a lot, because you can do mathematics with it. So let's say the number 10. For the light bulb on the circuits, I think it's a circle with a wave inside. Oh yeah, that's the way you should represent it. That is true. But yeah, I just tried to actually draw a little light bulb, but I'm pretty bad at this. But yeah, so let's think about the number 10. And right now we're in base 2, by the way. So 10 times 10, of course, is going to be 100. Right, we know this. And 10 times 10 is also 100 in binary, right? And this is why it's really important. Because or x inside a circle. Oh, I guess, yeah. Okay, makes sense. Because it allows you to deal with a universe that only has 2 digits, or only has 2 different states, in case of base 2. If you have something with 3 different states, maybe a ternary system is more useful. Because it allows you to just perform operations with numbers that make more sense in that particular environment, in that particular system that has those characteristics. So in this case of binary, our input, our data is going to be either 1 or 0, and it makes sense to make operations considering that duality of data, that it's binary. It's a binary system. Oops. If we had to do this in a decimal system, by the way, it would start becoming a bit more. It would start making a bit less sense in a lot of the situations because, for example, I don't know. Wait, let me think about this. So let's say you have this is actually a bit. It's difficult to think of a good example right now, but I'll do it. So just a normal. I don't want to talk a lot about memory because you guys because we haven't introduced it yet. But let's see. Okay, fine. So let's look at data. So binary data, right? So binary data is 1s and 0s, so it's base 2. So in base 2, the only digits are 0 and 1, right? Two digits. And we have, say, 2 bits of data, right? This is 2 bits of data. By the way, what is a bit? A bit is just shorthand for binary digit, right? So in this case, we have 2 bits of data, 1 and 0. And these were the inputs of a particular thing that we did, or sorry, the outputs of something. And this output is from, let's say that this output is from an addition of two different outputs. So you have an output that gave us 1. You have another output that gave us 1. And we summed this together. And this ended up giving us 10. Because 1 plus 1 equals 10. Right? In binary. When you receive this 10 output, if you want to make further calculations with this, or further manipulations, if you're doing it all in base 10, well, first of all, you already did a binary addition here, right? If you treat this as 2 instead of 10, you cannot, of course, you can't use 2 as an input for whatever other thing you're having. Because remember, if things take if things output binary data, they take input. They take binary data as inputs too, right? Electronic systems. So, and the binary data that they take as input as electronic systems is either the electricity passes there or it doesn't, right? So there's no way to input a 2 in this sort of thinking. So you'd have to convert this into something that is the same thing as 2, which is going to be 10 in binary. So it becomes pretty hard to do this. And that's why these, for example, the binary numbering system is really important and really useful for binary calculations, which is all the computers are really doing. So, so this is important. Now, again, for binary and counting in binary, it's just as easy as the rest. I'm just going to show you now because binary is pretty important, right? So you start with 0 again, right? 0, 1. There is no 0, 2, so this is 1, 0. Should have, yeah, 1, 0. 1, 1. And there's no 2, right? So this just becomes 100, right? Right? It's the same thing. Now, what really is important here is to realize that we have different bases for different purposes. And they're pretty useful, and it's important to understand what they are, right? So again, if we have 1011, right, this is actually going to be 11 in decimal. But how do we prove this? Well, again, we start with our base to the power of 0, base to the power of 1, base to the power of 2, base to the power of 3, and now we just perform the normal addition and we add it. The multiplication and we add it. So 2 to the power of 3 times 1 plus 2 to the power of 2 times 0 plus 2 to the power of 1 times 1 plus 2 to the power of 0 times 1. Right? Now, 2 to the power of 3 times 1 is 8. 2 to the power of 2, well, times 0, this is just 0. 2 to the power of 1 times 1 is 2. 2 to the power of 0 plus 1 is 2. Wait, this is wrong. It's 2 to the power of 0 times 1, which is 1. So 8, 10, 11, right? And this, of course, in base 10. And we can represent bases of numbers by doing a little subscript. So you can say, for example, you don't see it very often because it's really not done very often. There are very rare occasions where you actually need to show this because you are either working with one base or the other. But you can do this, and 2 is the same thing as 11 and 10. These are the bases. Okay, so we understand bases a little bit. I need to go work. Have a great afternoon. Thank you, man. You too. Have fun at work. Off topic. Do you know a way to make money passively online? Yeah, I really don't. I mean, you have ads, you have surveys, you have all sorts of stuff, but good money online only if you actually open up a company or something. I think I'm not entirely sure. I'm not the best person to ask for that, honestly. So yeah, so we took a look at bases. Now in base 60, by the way, right? So these are other applications. So we use time in base 60 because we consider that after, when we say time, I mean when we're dealing with the seconds, right? And so after 59 seconds, this becomes 1 minute, right? And again, so, and then 1 minute, blah, blah. So 1 minute, 25 seconds, 26, 27, until you get to 59. And suddenly you're at 2 minutes, right? And as soon as you get to 59 minutes and 59 seconds, the next step is 1 hour. So you see how this is the same thing as what we've been doing for base 10 or for base 4 or for base 2, right? The same concept, right? Except for base 60, you have 60 digits from 0 to 60. Once you pass that, you have to start using the, you have to, start the count again. So after 59, it goes 0. Now, in base 60, we actually represent things with these numbers. So it's a bit different because 59, you can consider it as a digit. But yeah, we do that. We work with other bases as well. But the most important thing to keep in mind is base 2, base 16, base 10, these exist and are pretty common in our day-to-day lives. Especially if you're a programmer, if you want to go into reverse engineering, you're going to deal with base 2 and base 16 more. Now, why is base 16 helpful? Well, it's kind of a little side note, but let's talk about what a byte is. A byte, if you look up in the definition, right, a byte is 8 bits. And what are bits? Well, a bit is a binary digit, right? Base 2 digit, so it's either 0 or 1. So it's 8 digits of either 0 or 1, right? So you can think of a byte as going from 0, 0, so 1, 2, 3, 4, 5, 6, 7, 8. Yeah, so 8 zeros into 8 ones. Right? This is the whole range of a byte. A byte can have 256 different values. Why 256? Well, because this is 256. And how do you prove it? Well, let's figure out what 1, 1. So what 8 ones in base 2 really is. So if we're doing base 2, again, this is 2 to the power of 0. I'm just going to write the number that it is instead of the power. So 2 to the power of 0 is 1, 2 to the power of 1 is 2, 2 to the power of 2 is 4, 2 to the power of 3 is 8, 2 to the power of 4 is 16, 32, 64, 128. Right? Now the result of this is going to be, of course, it's 1 times everything, so I'm not going to write the 1 times. So it's 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, right? Now, so if we do this, so 2 plus 1 equals 3, 7, so 15, 16 is 31, 31 plus 32, so 63, 64 plus 63, 127, so this is 128 plus 127, just 255, right? So we know that this is 255 in decimal, and it starts at 0, so it's 0 through 255, which is 256 values, right? So a byte has 256 possible values, right? Great. Now, this means that there are 256 different ways in which you can represent a byte. And if you have to write it in bits, it's going to be really, really difficult for you if you're doing this. Why? Well, because let's say you need to represent 20 bytes, and there's you need to work with 20 bytes, and you need to, let's say you're looking at a file that has binary data, and you need to kind of parse through it and figure out some patterns in it, and it just has, let's say, 60 bytes. Okay, 60 bytes, not a lot. But now, 60 bytes is not a lot, But when you consider that each byte is 8 bits, right? You certainly have, which what you have a very large number of do this, especially when we get it to, we're not necessarily complicated, but pretty long to actually represent it like this. So how can we represent it in a more compact way? What the hell? Screen mirroring? There we go. How can we represent it in a more compact way? Well, we can use other bases to represent those numbers. And so if, let's talk about base 10. We could use base 10 to represent the binary digit, to represent bytes. But there's a problem with using base 10 to represent bytes. So if you look at there are some kinds of calculations it's just not possible for you to do in your mind. Let's call up a calculator here. Some are just impossible, right? Oh, oops. Okay. So, the number 255. So one way that you could represent this, right, in decimal, right, is you can assign a number to it, right, and then you have less. So 0 would be 0 would just be 0. 1 would just be 1, right? And then as soon as you got into 10, for example, this would be 2, easy enough. And when you get to 1, 1, 1, 1, 1, this, which is 256, you just represent it as 256, right? And this is fine. It's perfectly fine. But it's kind of a problem because it's a problem because you don't get how do I say this? Let's look at it from the other perspective. So I mean, it is a problem because it's actually way more complex to work with than base 16, but it's not a problem because we can't do it. So if we look at base 16, we realize it's simpler to work with this, and it's better in a way. So base 16 makes it so that you can represent a sequence of 8 bits, any 8 bits, using at most only 2 digits. This is really important. So 0, 0 is 0. FF is going to be the last, so it's going to give you the, so if you, okay, let's do this in the way that we were supposed to. So, because doing math with this is not entirely, how do I say this, is not entirely, oh god, it's not really automatic. So let's count with this ourselves. So I never counted with letters before with you guys here, so this is why I think would be better to do it with the letters. So we know what happens up until 09, but then we don't go into, actually we go into the other digits, but 10 happens much later, right? This is the difference at base 16 because we haven't reached all the numbers. Remember, this is goes, so 09, then AF. So from here you still have 0A, you have 0B, you have 0C, you have 0D, and then you have 0E, and then you have 0F, right? And if you look at this, of course, 0F is going to be the last number, so this starts at 2, sorry, at 0. And I didn't write the other numbers, of course, but this will end up at 15, right? Oh, you can't see this. I'm an idiot. This will end up at 15, right? So after this is where you go into your 10, and you go into your 11, etc. And you repeat the same pattern over and over again. So And also, let me show you something that you might not know, because it also, if you want to mess around with values and stuff, it's way easier to also just go into Python and try to terminal. And you can actually represent hexadecimal by saying 0x, let's say, ff, which of course is going to be 255, or 0x 0e for something like that, or, you know, same thing. You can represent this. You can also represent binary numbers, so 10 in binary. So you use 0 and then x for hexadecimal, and then b for binary. You just put, or you can do int and also represent this. So let's say ff in base 16. It's the same thing. But yeah, this is just the idea that I wanted to put, to give you. Going to be from 0 to ff, right? Because ff is going to be 255, and there are only 256 possible values for a byte. Great. So this means that you can represent any single byte using 2 digits. This is huge, because it allows things to be incredibly compact, and the mathematics just flows normally as it always has. And it becomes incredibly useful. It becomes incredibly useful, especially when you have, for example, things like this. So you have, right, when you have like things like this, or, you know, any sequence that has a lot of that it's not just 1 byte, right? We're talking about many bytes. So we're talking about 4 bytes. We're talking about 6 bytes. We start getting big numbers, and if we were to do this in decimal, we would have huge numbers that we couldn't really work through very well. But with hexadecimal, things are pretty neat and tidy, right? Because you can equate 4 bytes for 4 bits for half of this. So you can always understand this as a byte, understand this, right? So it just becomes easier. And I can prove it to you as well. So the proof for this is really interesting. I mean, how would I prove it? There are plenty of ways to prove this. It's a bit of a side note, but okay, let's go with this. Right? What is this? This is 1,000. What is this? This is 100. What is this? This is 10. This is 1. Okay. So how many digits does this have? 1. How many digits does this have? 2. How many digits? 3. How many digits? 4. If you notice a pattern here, you'll notice that between these two, so between 10 to the 0 and 10 to the 1, the value, so the value that you need to raise 10 to the power of to give a number that only has 1 digit is going to be between 0 and 1, excluding the 1, right? Because 10 to the power, if you're considering whole numbers, we're just considering whole numbers, right? So 10 to the power of 0.999. So if we make this with our brilliant calculator here, so it's 10. So let's go 10. Where's the power thing? I just downloaded this. I've never used this particular calculator, so I still need to find the symbols for it. So, and I can't actually see this properly, but wait. Where on earth is it? Is it not here? Okay, let's just do this. 1 times 10 to the power of 0.99999, right? This is going to give you 9.999. So if you take the integer of it, it's just 9, which is the last digit, right? It's just 9, which is the last digit. Oops. And 10 to the 0, of course, is 1. So between 0 and 1, if you raise 10 to the power of that, it's going to give you from 1 to 9. and it's going to be a 1 whole digit. Now from 1 to 2, it's going to be 2, right? Because it's going to be from 10 to 100. And so all numbers raised to the power of those numbers from 1 to 2, excluding 2, is going to be always two digits used. So you can use this to generalize and to say that you can calculate how many digits you'll require for a particular number. So let's say, and we can do that, of course, with a logarithm. So if we say log base 10, and let's say right now, let's say 100, right? And if we pull out our calculator, this of course is going to be, so let's go, where is log? So log 10, of 100, it's going to be 2, right? Simple. And now here's the thing, we always have to round down here because, so let's say we do log 10 of, let's say 124. It's going to be 2.0 something, right? So we always have to round this down. And of course we also have to add 1 because as we start with 0, we require 1 digit. So then we just add 1 all the time. So we can, so this is essentially kind of an intuitive proof of how if we round, so log with our base, with our number, this is going to be equal, well, of course, again, if I do, for example, log base 10, right, of 199, sorry, not 199, log base 10 of 999, it's going to be pretty high up in there, right? So of course we have to do this, we have to do this plus 1, we have to round it. We have to round down, we have to floor it actually, not round it, we have to floor it, but it's the, so if we floor this is always going to give us the number of digits required for that particular number to be done in that particular base. So if you use this for base 2, for example, so let's say, for base 16. Our highest possible number, of course, in base our highest possible value in a byte is going to be 255, right? So of course, if we do this, so if we floor it, log base 16 of 255, and then of course we add 1, this is going to give us, and we can do this right now. Oh, can we? Can we change bases here? It's a really weird calculator. It does not allow that. Or does it allow it? I just don't see it. Where can we put our log base? It doesn't seem like we can. Seriously, TI-86 doesn't have this? Weird. Or maybe I'm just not seeing it. Maybe I'm an idiot, I'm not seeing it, but you know what, let's just use Google for a second. So log base 16. Wait, I was thinking that there would be some. Okay, can I just say, for example, log 16 of 2? I can. Okay, that's great. I can actually. No, I can't. Damn it. How do I do this? I thought the calculator would do it, but it doesn't matter. So in Python we can import math, and we can of course do math.log. And if we do math.log, just to show you that it's a thing. So base 16 of 16, this should give us 1, because 16 raised to the power of 1 is 1. So log base 16 of what we were doing before, which was 255 plus 1. And now we need to floor this, by the way. So math.floor this, and this should give us, oops, my bad. Wait. Why? Did I make something wrong here? Wait. Oh no, I did not. Never mind. I'm an idiot. Of course. Oh, what is log? Okay. Let's yeah. This makes perfect sense, and I'm an idiot. It's wait. So yeah, exactly. Okay. Perfect. Perfect. Okay. So if I do this, for example, this is going to give us 2. Okay, so it's the other way around, I guess. Okay, fair enough. So if we have 255 and 16, yeah, there we go. So plus 1, and we floor this. This makes sense now. I was considering, okay, so what is log? Okay, people are asking what is log, so this gives us 2. This is just like a curiosity thing. It's kind of off the point, but I'll show you what log is pretty simply. So, it's a very basic concept in mathematics. Well, at some point it would be. I'm just trying to figure out how to change template, and it's going to be blank dark. There we go. Okay, so let's say you have a number 2 to the power of 2 equals 4, right? Now, what if you didn't know this? Or let's say to the power of 3 equals 8. You know this, right? Because 2 to the power of 3 is 2 times 2 times 2, which equals 8. Right? Now, let's say you didn't know this. You have 2 to the power of something equals 8. Let's call it x. But you don't know what x is. Now, here you can see that x is 3. But what if you don't know what x is? Well, the response, what x is going to be the logarithm base 2 of 8 equals x. What this means is, so what the logarithm is doing, the logarithm is composed of 2 parts. So it's composed of a base, and it's then composed of your number. And having this is the same thing as saying, b, well, I should, b, well, let's say this equals x. B to the power of x equals n, right? It's the same thing as saying this. So we use it to figure out the answer to these kinds of questions. So if we have, for example, and this is something I can show you in the calculator more easily. So let's say we have 10 to the power of something equals 200. You want to know what x is. Well, you do the logarithm, base 10, so 10 to the power of x is going to be equal to 200. Right? And this is just a representation of it. So if you do this, it's going to try to figure out the result of this. It's going to try to figure out what number raised to this base equals this number. So 10 raised to what equals 200? Well, let's pull out our calculator. So we have our log. By the way, the log, when you don't have anything on the base, it's the same thing as saying base 10, right? So that's why here you don't see anything on the base. It's the same thing as saying base 10. So 200, this is 2.3. So this is equal to approximately, let's say, approximately 2.30, right? 2.30. Now, how can we test this? Well, now if we do 10 raised to the power of 2.30, it should be approximately equal to 200. Right? Let's test this out. If you do, so 10 to the power of 2.30, 199.52. Yeah, we didn't take all the digits from here. If we had taken all the digits from here, it would be exactly 200. But can you see the where we're getting to right now? So when I do log of something, I'm asking a question. So log b n. I'm just asking a question. What is the number raised to this base that gives this number? Okay, let's look at your example. So your example is we have x to the power of 4 equals 3, 4, 6, 7. Okay, now this is different because we cannot use the log right now. Why? Because, well, with log, what you're doing is you have a base, right? So x, you have a base. In this case, the base would be x. And you have 3, 4, 6, 7. So this would be how you'd represent it if you wanted to, right? So what are we doing? So we're doing the base raised to this power equals this, right? And we're now trying to figure out what x is. Now the logarithm, we have to specify a base. So we need to know what x is for here. So we can't do it. Well, what we could use log for is the opposite of this. So if you had, for example, 4 raised to the power of x equals this, and we tried to find what x is. So here we could say, well, log base 4, because 4 raised to something, equals 3, 4, 6, 7. What is that number? And then you can use log base 4 of this, and your calculator should have a way to switch bases in your log. I cannot find it here. It must have. I'm sorry, it must have. I'm going to try and maybe see if I can somehow. Okay, maybe I should try to wait. How do I? Am I an idiot right now? I am. Well, I don't know. I'll figure it out at some point. But you should have on your calculator. Oh, so we can't use log to know the x when we only know the raised? No. The way you would figure this out, you don't need log because you can figure this out in a different way. You can say, well, if you have, okay, let's do this again. It's easier because if you have if you have x raised to the power of 4, well, the answer is x is going to be equal to the fourth square root of 3, 4, 6, 7, right? And we can compute this too, and I actually have to look up the documentation for it, so maths square root docs, Python, square root, wait, I don't want the square root, I want the root, right? But I don't actually need to know this necessarily because I can just raise it to whatever power I want. But so the number that would be this would be so okay. It's x is this right is the fourth square root of this number, right? Now a way we can rewrite this is by saying that x equals 3, 4, 6, 7 raised to 1/4. Right, so if we do that, so if right now we do 3, 4, 6, 7 raised to 0.25, we're going to get 7.72 something, right? So we can get the x is approximately equal to 7.73, approximately. And you can test this because now, if you do 7, wait, let me, so 7.73, and you can test this because right now if you do, damn it, okay, if you do 7.73 raised to the power of 4, it's going to give us a number that is pretty close to that. But of course, if you use the actual number, it's going to give you way more precise evaluations. So let's use the actual number, and you can see 3, 5, 6, 7, right? So you can do it like this, and you don't need to go into logarithms because you can't use the logarithms in this scenario. But are you getting the idea or not really? Got it. Okay, that's good. I had a couple of different ways that in my mind that I thought about to explain this in case you didn't. But okay. So um, so just to finish up, um, why was this logarithm important? Well, because now we can ask what the logarithm of any particular base is for a specific number, and we can add 1, and we can floor this. And this is going to be equal to the number of digits needed to represent it. What do I mean? Oh yeah. Okay. Let me just finish this up, and I'll touch on that point. It's interesting to know as well. So, what does this mean that I'm saying right now? What I mean is, so let's say we have 255. It's a number, and this is in decimal, right? So 255 decimal, and we want to know in base 16 how many digits would this take to represent. We can use this. So we can say, we can floor. Floor just means to round down, okay? So if you have 2.8, this equals 2. 2.1 equals 2. So we're rounding down. That's what it means to floor. So we're flooring the logarithm of base b. In this case, I want base 16 of the number 255, which is in decimal. And then we add 1. By the way, this is one operation. Like the logarithm of this, and then we add 1. Or you can floor it and add 1 afterwards. Doesn't matter. So, oh, CMD in the front, sorry. Okay, so so as we do this, so let's do this with our Python. So I'm gonna quit just so I can do this. Okay, so let's import math. So because math is going to be used to floor, so math.floor. So this is going to floor this, and we're going to have math.log of 255 in base 16. Let's just do this. This is 1. But remember, we have a plus 1 here as well. So it's this plus 1, which is 2. This is the number of digits needed to represent this number in base 16. And it's true, because this number is FF. Right, so this is the way you can prove how many digits you have to use to represent a particular number in any base. Right, and this is I guess a little side note, because with simple numbers, of course, couldn't be math.seal instead of adding plus 1? Well, if you seal this, right, okay, of course without the plus 1, this would still be 2, right? But here's your problem. You see the difference? If you seal this, this becomes 2. 256 becomes 2. And why? Because the log of 256 base 16 is exactly 2. Right? So when you're sealing this, it just becomes 2. And you don't add the plus 1. But 256 actually requires 3 digits. As we can see, if we use our original formula, it's going to give us 3. It requires 3 digits, because obviously it's after FF, right? And FF is F is the last digit of base 16. So 0FF, after this, you have 100, you have 3 digits. So the math.seal doesn't work when you have integer numbers as results of the log. The reason we do the floor is because we don't actually have to necessarily floor this, but I mean, we obviously we do have to floor this to get the result we want, but yeah, but that's why the sealing doesn't work. The seal always works if your numbers are not integers when as a result. Why? Because if your number is not an integer, so let's say it's a 0.9, so let's say that the result is 0.9, right? It's going to seal this into 1, and that would be the result, because the floor of this would be 0 plus 1 in the original formula. But if the result is 1, the ceiling is still 1, but the result in the previous formula, the floor would be 1, so the result would be 2. So there would be a discrepancy, right? And I should have explained this in a better way. Let me just do this in this way. So let me do it with this. It's easier. So let's do math dot actually let's just do a math.log, and let's do 256. Sorry, let's do a different number. Let's do 10. Sorry, not 10. Let's do 9, but in base 10, right? And we all know that the number 9 in base 10 requires only one digit. The result of this is 0.9, 0.95. If you floor this, it's going to be equal to 0. If you seal this, it's going to be equal to 1. Now, if you proceed to flooring this, you have to add 1, which is going to be equal to 1 at the end. So these two values are the same. But if we go for the number 10, which we know requires 2 digits, right? It's the number 10. The result is going to be exactly 1. If the result is exactly, if the result is exactly 1, if we floor it, or if we seal it, this will be 1, right? But when we floor it, we also have to add 1, so this becomes 2, right? But this is still 1. So it's the wrong number, you know what I mean? And that's the reason why we have to floor it and add 1 instead of just sealing it. Yeah, you're probably never going to have to use this, but it's a nice thing to know. Because even if you cannot immediately calculate what number would a particular number be in a different base, you can at least know how many digits you'd need. And for bytes, you can use from 00 to FF in hexadecimal, and this will represent all 256 possibilities of bytes. And of course, you can also think of a byte. So if a byte is 7 digits, if a byte is 8 binary digits, so 8 bits, and bits are only 0 or 1, so there are only 2 possible digits. The whole possible space of a byte has to be 2 to the power of 8, right? Which is exactly 256. So another way to think about it. Oh, thank you for following NightCallX. Really appreciate it. So yeah, so this is base. These are bases, and they're pretty important as well. But there's not much more to this. I may have expanded a bit more into this than is needed. You don't really need to know that much about bases to successfully use them in everyday operations. So the only thing left is virtual environments. And and by the way, how much bytes is in FF? Yeah, that's okay. So sorry, I don't need the board for that. I can use Python. So so you can type it like this, and you can have 255. But here's the thing. So how many bytes is in FF? That's a great question. Well, FF is a 255, which is if you do in binary, if we do it in binary, it would be a series of 8 ones, right? So 8 digits, 1, right? So this is still 1 byte. And so in FF, there's still 1 byte, right? So let's say, because of the definition of byte, a byte is 8 bits, right? And a bit can be 1, and a bit can be 1 or 0. So this is a byte, right? But this is also a byte. This is also a byte. Well, to be fair, fine. If we include all the 8 possible digits, like this is a byte, right? this is a byte, this is a byte, this is a byte. It just so happens this is the last, is the highest byte, I guess, right? You ask for bytes? Yeah, right? So when you have, for example, let's say you have, yeah, exactly. So FF, so if FF represents a byte, FF represents 2 bytes, so 3 bytes and 4 bytes, and so on, right? But again, it doesn't have to be FF. If we're always doing it in base 16, so 0xFF, this, oops, 0xFF is still 1 byte, right? FF is another byte. So 2 bytes. 3, 4, right? You can have, say, FF0E, right? We still have we still have 2, etc. And yeah, of course, and yeah, if you do FF, you have in here and 1 byte. If you do FFFF, you have 16 bits. So think of it in this way. Let's say, so this, yeah. So, okay. Wait, this is not what I meant. I meant this. There we go. So, wait, do we have the opposite? We do. Okay. So for example, okay, F5, right? F5 is this. If you notice, this is 1, 2, 3, 4, 5, 6, 7, 8. Now let's say F5 and then we have CD. It's another byte, right? You'll notice now 1, 2, 3, 4, 5, 6, 7, 8. And then 1, 2, 3, 4, 5, 6, 7, 8. So we have 16 bits in total. And a byte is 8 bits, so we have 2 bytes. Right? So if you keep adding things, so you have E5, you're going to have another sequence of 8 bytes in front of it, of 8 bits in front of it. So it's 3 bytes, and we have DD. It's 4 bytes now, right? So it's if you put them together, it's still going to be different bytes, because all you need to represent a single byte is two hexadecimal digits, and this is why hexadecimal becomes really useful when correlating it to bytes, because it's really simple. 1 hexadecimal can be used to represent 4 bits. Right? So this we have 4 bits. So if you have right, so 0f, you can still have a byte if you pre-appended everything with zeros, right? So if you do, for example, bin 0x0f, you have 1111, which is 4 bits, right? But the maximum possible representation of 2 characters is a byte. But sure, if you have 0xf, right, you can say that this is not a byte. It's half a byte, right? But surely if you do this, it's not pre-appending it, right? But again, if you do hex of 0b, oops, this, it's still going to be 0xf, and this is a byte technically, right? It just has zeros there. But yeah, hopefully that was understood.